Imagine, for a second, trying to manage a massive, sprawling highway system. But here's the catch. You don't get to tell the cars where to go. You can't just build new lanes on demand. And if a bad traffic jam happens, the entire national highway network could instantly collapse. Well, that's exactly the invisible, high-stakes struggle of managing our modern power grids in today's deregulated electricity markets. Welcome to this explainer. We're going to decode the fascinating collision between free market economics and the unbreakable laws of physics. It's the ultimate balancing act that determines if your lights actually stay on during a heat wave and, of course, exactly what your power bill looks like at the end of the month.
Okay, let's dive into this. How exactly do you build a free market for electrons? I mean, really think about it. In a normal market, if I buy an apple from you, you just hand me the apple. Simple, right? But here, we're trying to financially trade electricity. And that is a product completely governed by the rigid, mathematical laws of physics. You can't just box up a megawatt and ship it via FedEx. It has to flow instantly across physical wires at the exact millisecond it's needed.
To understand how we pull this off, we have to look at the deregulated electricity market itself. The absolute most critical aspect here is the separation of powers. You know, back in the day, a single utility owned the whole shebang, the power plant, the wires, the meter on your house. But deregulation split all that up. So now power generation is completely separated from transmission. This allows buyers and sellers to trade energy financially, all chasing that ultimate goal of cheap, competitive power. But as you'll see in a minute, that financial goal is constantly wrestling with the physical reality of the grid. So here's our roadmap for today. First, we'll look at the deregulated power market. Second, gridlock, congestion and limits. Third, the hardware fix, facts. Fourth, the software fix, simulations. And finally, powering a competitive future.
All right, part one, the deregulated power market.
In a perfect, highly competitive, deregulated market, the price of electricity is based on short-run marginal cost. Basically, that's just the cost of producing the very next megawatt of power. And it's driven by three main things: your fuel price, your generation efficiency, and your day-to-day operations and maintenance costs. Now, obviously, real markets aren't perfect. Power plants also have to cover massive fixed construction costs, which means generators offer capacity at all sorts of different prices. But the whole point of competition in financial contracts is to drive prices down and keep them as close to the short-run marginal cost as physically possible. Moving on to part two, gridlock, congestion, and limits. So here's the fundamental flaw in trading power. Electrons, they do not care about your market contracts. If a buyer in a major city buys incredibly cheap power from some distant seller way out in the country, those electrons aren't going to take a neat, direct path. Because of the laws of physics, electrons are kind of like water spilling down a hill. They just take the path of least resistance. And this causes what engineers call loop flows, basically involuntary surges of power that force their way through unexpected and frankly under-equipped transmission lines, causing some serious congestion. To manage this congestion, independent system operators use a metric called available transfer capability, or ATC. When a transmission line gets congested, its ATC drops. And if that ATC drops to, say, just 15% available, it means the network is hitting its thermal limits. The actual physical wires are literally getting so hot that they start to sag. When this happens, it completely stifles free competition. Because honestly, it doesn't matter how cheap a financial transaction is, the power simply cannot physically fit on the line. The market is gridlocked.
Which brings us to section 3, the hardware fix, facts. FACS stands for Flexible AC Transmission Systems. These are advanced, static power electronics-based devices. You could think of them as the ultimate smart grid hardware. In a deregulated environment where power flows are super unpredictable, old-school mechanical switches are just way too slow. FACS devices step in to provide high-speed, continuous control over the grid. They do this by rapidly altering voltage levels and transmission line impedance. So they basically act like a high-tech valve to dynamically push or pull power away from those congested lines.
The original mandate from the Electric Power Research Institute states their objective pretty clearly. FACS must, quote, increase the transmission capacity and control the power flow over designated transmission routes. In our deregulated market, this specific hardware is exactly what allows us to squeeze every last drop of efficiency out of the infrastructure we already have, saving us from spending decades and billions of dollars building new transmission towers. Now, what's really interesting about this slide is how engineers rigorously compare these devices. Take a look at the SVC, or static var compensator, compared to the STATCOM. Notice the parameters they're judged on here: compensation accuracy, response time, and harmonics. While both are incredibly useful, the STATCOM is rated excellent for control flexibility and boasts a very fast response time compared to the SVC. Engineers rely on this exact kind of data to drop the absolute perfect piece of hardware right into a specific grid bottleneck, which directly enables a higher volume of free market energy trades.
That leads us to part 4, the software fix simulations.
Solving gridlock actually requires two halves. On the hardware side, sure, you have the physical installation of multi-million-dollar equipment actively pushing power around. But on the software side, that's where you have continuous mathematical optimization. These are the insanely complex simulations that decide which generating plants should turn on and off, which is known as unit commitment, and they predict exactly how power will flow across the grid long before the financial trades are even finalized.
So this begs a pretty massive question for anyone managing a deregulated market. How do independent system operators, the folks actually running the grid, predict the future? How on earth do they know that a trade made today won't literally melt a wire tomorrow?
Well, they do it through a relentless, step-by-step digital simulation process. Step 1 is the power flow study, which calculates the exact loading on transmission lines based on current demand. Step 2 is short-circuit analysis. This runs scenarios to ensure protective relays will instantly clear faults if, say, lightning strikes or a line suddenly drops. And finally, Step 3 is economic dispatch and unit commitment. This is where mathematical optimization techniques like mixed integer programming find the absolute least cost combination of power plants needed to meet the load. It is a constant 24/7 balancing act between extreme physical safety and rock-bottom market prices.
And finally, Section 5, powering a competitive future.
The simulations we just talked about, they aren't just theoretical. Regional transmission organizations rely on some seriously heavy-duty software packages. We're talking General Electric's MAPS and MARS, Hitachi's ProMod, Siemens PSSE, and ETAP. These incredibly sophisticated systems analyze load flows down to 5-minute intervals. They're what actually allow regulators to plan multi-year expansions, seamlessly integrate completely unpredictable renewable energy, and run near real-time wholesale markets securely without accidentally triggering rolling blackouts. Literally, they are the invisible brains of the deregulated market.
So, we've seen the financial ambitions of deregulated markets, the physical realities of electron loop flows, and the incredible hardware and software solutions we built to bridge that gap. But I want to leave you with this final thought. As power markets continue to expand, as we add massive amounts of variable renewable energy to the grid, and as our overall demand for electricity just skyrockets, will our mathematical software and fax hardware always be able to stay one step ahead of catastrophic gridlock? It's arguably the most critical balancing act of our modern era. Thanks for joining me for this explainer, and remember to keep questioning the systems that power our world.